All right, so now we are starting our chapter in electrochemistry, uh, and uh, and electrochemistry centers around redox reactions, oxidation reductions, and as you probably recall from Chem 200, when something is oxidized, it loses electrons. And that name historically comes out of the fact that most things that react with oxygen tend to lose their electrons. But in the most general definition of oxidation, oxygen can lose its electrons. So even oxygen can be oxidized by something that's more electronegative, for example. So oxidation is kind of a historical name. It came out of doing lots of experiments involving oxygen and finding out that most elements that combined with oxygen were oxidized, like iron, copper, metals and things. Now, reduction, as you remember from Chem 200, is when something accepts electrons. So where does the name reduction comes from? That comes from the fact that when something is reduced, it accepts electrons, and what is being reduced is its oxidation number. So the oxidation number, whatever it is, um, decreases. And so that's a sign that it accepted electrons and its oxidation state went down. And it's kind of weird to think that when something accepts another thing, then a quality about it is reduced. We always think, well, it should be enhanced. But the reason why the oxidation state goes down when it accepts electrons is simply due to the fact that Benjamin Franklin defined the electron as having a negative charge. So it's accepting something that's negative, and so the oxidation state goes down. Uh, Now, you have to think about maybe the makeup of the atom that you learned in Chem 200. So, for example, hydrogen has one proton and one electron. So the number of electrons it should have to be neutral is one electron. And when you pair that up to the number of protons, they equal, and so they cancel each other out and it's not charged. Now, if you have, let me just write up here. So I have hydrogen um, that has one proton and one electron. So it's not charged, it's neutral, and its oxidation state is zero. And so I put a zero and I circle it, as opposed to a hydride that has an extra electron. And so it has two electrons. That's one more than the number of protons. So its net charge is -1, and its oxidation state is also -1. And you know the deal for this guy, it would be +1. So the reason why I circle my oxidation numbers is because I don't want to get them confused with the overall charge of the molecule that maybe I'm assigning oxidation numbers to. And so you ask, well, geez, why do we have to know anything about oxidation numbers? Well, because you're going to have to distinguish between reactions that are redox reactions, and redox reactions involve electron transfer. So this is a redox reaction here, as opposed to other reactions which are, not oxidation reduction. In this case, this would be uh, an acid-base reaction. Now, how do I know one from the other? Does anybody know how to distinguish whether I'm dealing with a reaction involving an exchange of atoms, or I'm dealing with a reaction that involves a redox? Anybody know how I would know that? All right, good. Um, that means you're about to learn something, which is the way to tell whether a reaction is a redox reaction is you have to assign oxidation states and see if they change. If the oxidation states change, then you know you're dealing with a redox reaction. Something in there accepted electrons and something in there um, gave up electrons. If the oxidation states don't change, then it's not a redox reaction. So let me show you what I mean real quick here. I'm going to assign the oxidation states in the first reaction and in the second. So now this hydronium has an overall charge of +1, and the oxidation state of oxygen here is -2. So I circle it because I don't want it to get confused with the overall charge of that. And hydrogen almost always is +1. Uh, Fluoride -1. In this case, it's -1. Here's +1, -2, and +1. So you see all the oxygens have the same all the hydrogens have the same oxidation number, which is +1, and all the oxygens have the same, which is -2, and all the fluorines have the same, which is -1 oxidation state. So nothing changes. All right, let's check out the one below and assign oxidation states here. Zinc is just a metal, so it has just as number of protons as electrons. So its oxidation state 0. I got +1 here. Zinc is +2 in this state. And over here I have hydrogen molecule, which is 0. So I see that hydrogen um, went from +1 to 0. So it was reduced. So what does that mean as far as accepting or losing electrons? Does anybody know? Reduced means, okay, you have to remember that.
Accepting.
Yeah, accepting. Thank you. Accepting electrons. And so you just have to start remembering it. Now, reduce, look at it. Look at the oxidation state. It went from +1 down to 0. The oxidation state was reduced. So that's where the name reduction comes from. Oxidation, that comes from historically things reacting with oxygen and lose electrons. So in oxidation, the oxidation number increases. And I see that here because zinc goes from 0 to +2. And so we recognize this reaction here as an oxidation reaction, whereas this one is not. Any questions on that? Okay. So here's the rules for assigning oxidation numbers. So you have to memorize these and practice them. So why don't you take a look at the rules now and see if you have any questions on what those lines are saying. So rule number 1, it says for atoms in elemental form, the oxidation number is always 0. So, for example, for copper metal, um, that's oxidation state 0. For phosphorus, it exists in a dimer, not a dimer, a polymer of 4 atoms. Each one of those phosphorus atoms has the same electronegativity. So in their bonds, they share the bonding electrons equally. And it turns out they have just as many electrons as they have protons. So each one of those phosphorus atoms has a charge of 0, just like oxygen. Now, you know what oxygen looks like as far as a Lewis structure from Chem 200, right? So here's an example of what I'm talking about. This is what I explained with phosphorus. Sulfur is another one. Any of the homonuclear diatomics. So I have these electrons, and I have some core electrons for oxygen, and oxygen is in row 2, so it has 2 core electrons. And this guy gives 2 more, so that's 2, 4, 6. And then there's 4 electrons in the double bond, which are shared equally because both of them have the same electronegativity. They're both oxygens. So they split those 4 electrons in half and get 2 each. So it's 2 in the core, in the the 1s2. That's 2. Then I got 4, 6, and then 2 more is 8 electrons for each one of those oxygens. And that's how many a neutral oxygen has. So each one of the oxygens in O2 has a oxidation state of 0. Any questions on that? All righty. The next rule for monatomic ions, the oxidation number equals the charge on the ion, and that should make sense, right? So this atom, copper here, lost 2 electrons, so it has 2 more protons than electrons, so it's a +2, and its oxidation state is also +2. Now, for oxygen, it's almost always -2, except in peroxides. For example, if I have like a hydrogen peroxide or a lithium peroxide, hydrogen can only give up 1 electron. So these hydrogens over here are both +1. That means the oxygens have to divvy up those 2 electrons. So each one of those has to have a -1. So oxygen is almost always a -2, except in peroxides and in cases where there just isn't enough electrons to be given, so it gets -2. All right, now hydrogen's almost always +1, except when it bonds with a metal, then it has a higher electronegativity than the metal, so the oxidation state of hydrogen is said to be -1. Fluorine is -1. Usually the halogens are all -1. Now, the last few rules, these two are the summation rules. This allows you to assign the oxidation states of all the other elements not talked about up here, all the other ones, by these rules. And the rules are simple. It says that if the compound is neutral, then all the oxidation states of the elements in that compound have to equal 0. And what this guy says is, well, if it doesn't equal 0, then it has to equal whatever that charge is of the ion that you're assigning oxidation states. So let me show you what I mean by looking at a few examples here. All right. Let's assign some oxidation states. And by the way, in chemistry, you probably have noticed this, that there's many ways to assign electrons to something. For example, when you were doing Lewis structures, there was a thing called formal charges, and there was a formula for assigning electrons in formal charges. There's other ways to do it too. There's the delta, or the partial charge, where you can use first principle calculations to estimate charges on atoms. There's the oxidation states. They have the rules that we just went over. Now, when you look at it at a molecule, does it really have these charges? If I looked at water, for example, I know from those oxidation states that this should be +1, +1, and -2. Now, if I did a study that looked at the electron density of, these orbitals and things like that, and divvied up the electrons. In reality, would oxygen get uh, 2 extra electrons, and would the hydrogens lose a whole electron? Of course not. It doesn't work that way. Oxidation numbers is just another method to keep track of electrons, and it's used a lot in electrochemistry to tell, for one thing, whether you're dealing with a redox reaction or not, and helping you balance, as we'll see, redox reactions using the half reaction method. So that was just kind of, I was going back and trying to explain that there are other ways to assign electrons to atoms in molecules and by themselves. But this is one way, and this is the way that we're going to be using. All right. So anyway, let's do this one. KMnO4. Let's do Na2C2O4. Let's do some polyatomic ions. C2O7 2 minus. PO4 3 minus. Anybody have any ones they want to do? How about one more? Oh, this is chromium here. How about just CO2? All right, so now I'm going to use the rules to assign oxidation states for these compounds, molecules, and polyatomic ions. Okay. So the first one, potassium's in group 1 metal. It's probably um, +1. But anyway, I know that MnO4 is a -1. So I know that that has a charge of -1, this whole thing here, because I memorized the permanganate polyatomic ion. So I know from the summation rule that if this is -1, then this has to be +1. Okay, but let's pretend I didn't know that. Okay, I'm going to go do my rules here. This is -2 from the rules, and I have to know that potassium is +1 from what I just said. Otherwise, I can't solve this. So you have to know that the permanganate ion is MnO4 minus, or you generally have to know that group 1 metals, they only have 1 electron that they're going to give up. And then if they're going to give up other electrons, it's core electrons, and they're down closer to the nucleus, and they're going to be held much tighter and not likely to be given up. So this forms the stable octet. So for group 1 metals, you can assume that they're going to be +1. Group 2 is +2 when they're combined with uh, other species. So anyway, now I have the summation rule. It says +1 -8, because there's 4 oxygens at -2, plus something has to equal the overall charge, which is 0. Okay. So what does that plus have to be? +7. Okay. So that should make sense now. If you take it apart and just look at the permanganate, we can do that again. This is going to be -2. That's going to be -8 total. So this has to be +7 in order to equal an overall -1, which is the charge. Okay. Any questions on that one? Okay, let's move on to the next one. Sodium oxalate you used in your experiment. minus 2, according to the rules. Sodium is a group 1, so that's a plus 1. Hydrogen can be here as well for oxalic acid, and hydrogen H2, that would also be plus 1, so it's just like sodium. And now I have a plus 2 plus a question mark minus 8 equals 0. So I have 5. And so each one, this is going to be 5, right? Question mark equals 8 minus 2. Oh, sorry, 6. 6. And there's 2 of them, so each one is going to be plus 3. Any questions on that? Okay. All right, let's do the dichromate. Oxygen, there's 7 of them in dichromate. Each one is going to be minus 2. So that's minus 14. That has to equal a minus 2. And so I have to add up 2 times the charge on chromate, which is X. So I get 12 divided by 2 is 6. So it should be a plus 6. Okay. In other words, 2 times 6 minus 14 equals a minus 2, which is this. So what I'm doing is I'm just using that summation rule back here that says that the sum of the oxidations on a polyatomic ion equals the charge of that ion. So here's the sum of the oxidation states. There's 2 at plus 6 minus 14 because there's a minus 2 and there's 7 of them. So I'm adding up all the oxidation states of the oxygens, all the oxidation states of the 2 chromiums, and I'm getting the overall charge of the polyatomic. Any questions on that one? All right. Let's see if you guys can help me do this one. What's the oxidation state on oxygen?
-2.
Okay. And so can you figure out the oxidation state on phosphorus?
Five.
Yeah. Let's check it. I got a 5 minus an 8, which is 2 times 4, equals a minus 3. Yep. All right, how about this last guy? What's the charge on oxygen?
-2.
Mhm. And so what's the charge on the carbon?
+4.
Yeah, thank you. So any questions on that? So that's how you use those rules to assign the oxidation states of all the elements. And so really, it's you just base off of very few of the rules. You know, one of the rules that I didn't have here, I probably should have, was the rule about the group 1 and 2 metals, but I think they're kind of more obvious. So maybe not. Maybe I should write that down there. All right. So this next plate introduces those terms that you may remember from Chem 200, oxidation, reduction. We talked about the historical terms for oxidation. We talked about the oxidation number being reduced when something gains electrons. Then this shows that um, loss of electrons and the gain of electrons. And so you have to have them happening at the same time. Electrons can't just disappear. If something loses them, they got to go somewhere. Uh, the other thing that you may not be so familiar with is this agent formalism. So an oxidizing agent or a reducing agent, they often use this in publications referring to molecules or other reactants. And the key to remembering the agent formalism is it's the opposite of what gets done to itself. So if it's an oxidizing agent, that means that that species is going to oxidize something else. So it itself gets reduced. So let's check it out. H plus causes zinc to lose electrons. So H plus is reduced, but it's called the oxidizing agent. Okay. And zinc gives up its electrons to hydrogen. So you can look at it from the perspective of zinc and say that zinc is forcing hydrogen to take electrons. So zinc, even though it gets oxidized, it's called a reducing agent because it gives its electrons to something else. Any questions on this formalism, the agent? Okay, so you'll run up against that here and again. Okay, this is just a recap of the stuff that we talked about already. And now we get into the types of oxidation reduction and why we can distinguish between those two different types. Direct redox reaction is something that you can easily find in nature, like rust is a direct redox reaction. It's when the reactants come in contact with each other. So they touch each other. So iron comes in contact with oxygen and gets oxidized. And in this case, the copper comes into contact with the silver and it gets oxidized. I looked this up on YouTube. So let me see if we can go check out that that thing, if I can get it to work. It'd be nice. All right, so this is a commercial. We don't need to, well, I guess we need to get through it. So in this YouTube video, they take a tree made out of copper. So it's a copper sheet that they cut and they made like a tree and they put it in a beaker. And now they're going to add silver nitrate to it. So this is an example of a direct redox. So the copper metal is in direct contact with the silver nitrate or the silver +1 ion. And so what happens is that there's a natural flow of electrons from the copper to the silver ion in the solution. So the silver ion in the solution comes out of solution when it accepts the electron from the copper and crystallizes on the copper. And so you get this silver um, crystal solid coming from solution on the copper, and the copper dissolves into solution. So you see that liquid around the Christmas tree, it went from clear to a blue, indicating the presence of copper 2 plus ion. So this is an example of a direct redox reaction, much like um, rust in your car. Okay. Now, an indirect uh, example of a redox reaction is the batteries that you're going to build or you have built in the lab, the last in lab experiment in electrochemistry. You're going to be making up voltaic or galvanic cells. Now, um, this is particularly interesting. So you have, again, a redox reaction taking place, but you separate the places where they happen. So in that video, we saw that the copper and the silver were in the same beaker. But what if we put the copper in one beaker in its solution, just copper solution, and in the other beaker, we put the silver, and we connected the two beakers with a wire? Then again, delta G is going to be negative, just like the spontaneous reaction we saw in the direct example. There's going to be a flow of electrons from the copper to the silver naturally, and the silver is going to be reduced. But the difference is with the direct setup, you can't easily tap into this natural flow of electrons, this Gibbs free energy that's out there, the energy of the battery. But in the indirect, you can tap into it in that wire. You can put a light bulb in there or a motor, and you could run that from this natural flow of electrons from higher potential to lower potential, or from the copper to the silver side. And so that's the idea for um, the voltaic or galvanic cells. Now, the electrolytic cell, this one, the difference between these two, you probably don't know. The electrolytic cell runs a spontaneous reaction in reverse. So it runs non-spontaneous reactions. So this is delta G is positive. And for these guys, delta G is negative. So say I wanted to run this reaction in reverse, um, and I wanted to reduce copper and I wanted to oxidize silver. I can do that. I just need to hook it up to a battery, as we'll see, with a higher voltage difference than this one would give. And that'll run it in reverse. So that can be done. And that's called the electrolytic cell. Other applications, you find redox reactions in biological systems. You know, blood carries oxygen, and iron is important in the heme group. So you'll study that. We mentioned batteries and rust, so redox reactions are important in those, and we want to look at that in a little more detail. But before we get to the batteries and the rust and electrolytic and voltaic type of situations, we're going to have to learn how to balance these redox reactions. And in Chem 200, you learned how to balance reactions using the method of inspection. You just looked on the left and the right side of the arrow, and you made sure that the number of atoms of a particular type were represented on both sides. And so we called that the conservation of mass, and that was good enough for Chem 200. Okay. But for redox reactions, we have to build in one more thing, which is we have to make sure that electrons don't disappear, that they, in fact, are accounted for. For example, in that redox reaction involving silver and copper, you might think that the balanced redox reaction could look like this. Okay. And at first glance, not having had Chem 200 in a while, you might say, oh yeah, okay, that's balanced. But it's not balanced by charge, because this copper lost 2 electrons. And this silver only gained 1. So what happened to that other electron? It just disappeared. So this isn't balanced. Um, and so we see we can balance this by putting a 2 here and a 2 here. Now this redox reaction is balanced. And I know it's balanced because of two things have to be true. The atoms have to be represented in the same number on either side. I have 2 silver on the left, 2 silver on the right, 1 copper on the left, 1 copper on the right. And I have to have a charge balance. So the charges added up on the right have to equal the charges added up on the left. So here I have a net +2, and over here I have a net +2. So the charges are balanced. So I know now that that reaction is in fact balanced. Now this was a very simple case. But how would you balance that redox reaction that you did in lab involving the permanganate and the oxalate, where you get the 5-to-2 ratio? How do you balance something like that? It's hard to just look at it and do it. So the method for balancing, to making sure that both of these criterion are true, is to balance using what's called the half reaction method. And so that's what we want to go through now until the end of our session, and then we'll call it quits. Okay. All right. This is another reaction. We just looked at the silver one. This one you can look at as well. It's tin plus iron goes to tin 4 and iron 2 plus. So first we recognize that it's a redox reaction because we can assign the oxidation states and see them go up and down. And then we can split them into their half reactions. So the half reaction method really is a method of dividing and conquering. So you handle the half reactions, the reduction involving the electrons, and then you handle the oxidation half reaction, and half reactions involve electrons. So they show electrons. That's what half reactions do. And sometimes the reactants, in the case of the reduction half reaction, and sometimes they're products, these electrons, in the case of oxidation half reactions. So again, we have this reaction. We know that it's a redox reaction. I can assign the oxidation states to everything here. +4, +2. And I see that tin loses 2 electrons, and iron here looks like it gained 1 electron, right? But there's 2 of them, so that's a total of 2. All right, so I see which species is being oxidized, and I can split that into the oxidation half reaction, and I see which reactant is being reduced, and I know what they go to on the other side, so I could make those products. And then for the half reactions, I would put in those electrons that are lost and gained. Okay, so that's what a half reaction is. Now, how do I use this half reaction idea to balance? Well, that's where the half reaction method comes in. And so here are the steps for balancing using the half reaction method. So the first thing you need to do is write down the 2 incomplete half reactions, something like we just did. So in order to do that, you have to assign oxidation states and identify what's being oxidized and what's being reduced, so you can break them up. And then step 2 says you can balance the elements other than hydrogen and oxygen first, and then balance oxygen with water, hydrogen with H+. That's step 2. 3 is balance the charge with the electrons. If it's a redox, the electrons go on the left. If it's an oxidation, they go on the right. Then you might need to multiply through by some factor to balance the number of electrons lost and gained. That's step 4. And then step 5, you add up the half reactions to get your overall redox reactions. You simplify any like compounds on either side. You check the charge to see that both sides have the right coefficients, and you check the atoms to see if they're represented in the right numbers on either side. So number 5 is an add up and check kind of thing. So here's an example of balancing using this half reaction method. So I have to balance this, and it says balance it in the presence of an acid. So it's in an acid solution. And by the way, these are the steps back here, 1 through 5. This is the steps that you would take to balance in an acid solution. Okay. All right. So the first thing I want to do is assign my oxidation states. So I'll use my rules that I just learned to assign those. They'll be -2. So that's a -4. The whole thing has to be +1. So this has to be +5. Zinc is all by itself, 0. Oxygen -2. The whole thing's +2. So this has to be a +4. And over here I have +2. Any questions on that? Okay. Now I see that the vanadium went from +5 to +4. So that was reduced. Its oxidation state went down. And I see that the zinc went from a 0 to a +2. So this was oxidized. So I assigned my oxidation and reduction half reactions. Okay. Now I go to step 2, balance all non-oxygen hydrogens. For the oxidation, it is balanced. There's only zinc, and so it's balanced. I don't need a coefficient. For the redox, The vanadium is already balanced, so I don't need a coefficient for that. So then I go to A back here. Now, I just balanced the vanadium and the zinc. And now I'm going to go to the next steps, which is balance oxygen with water and balance hydrogen with acid H plus. Okay. Oops, sorry, I'm going the wrong way. All right, so now I go to the next step and I balanced. In this one, there was no oxygen, so I didn't need any water. And since I didn't need any water, I didn't need any hydrogen. So I didn't need H2O or H plus for this guy. But for this guy, I see I have oxygen, two of them on the left, one on the right. So I need to add a water here. And if I add a water here, then I have to add an acid over here to balance those H pluses. And so I'm just going down the steps for balancing using the half reaction method. All right. And now I'm going to go to the next step, which is to balance the charge. So I go back to the oxidation and I see that I need to add electrons on the right because it's oxidized. And for me to balance the charge, in other words, I have a zero charge net over here. I need a zero on this side. So I'm going to need to add two electrons because -2 and a +2 is 0. And I can do the same thing here. I see I need a +2 net on this side. I got a +1 and a 3 more. So that's +3. So I need to add one electron on the reduction side. Now I see that there's a disparity between the number of electrons lost in the oxidation versus the number of electrons gained in the reduction. It's 2 to 1. That's no good. I could fix that by multiplying through by 2, which I do. So I multiply through the whole thing by 2. And then I go to step 5, which is to add them up. So when I add them up, I get the overall balanced, hopefully, redox reaction. And in the overall balanced redox reaction, you don't see the electrons anymore. They get canceled out. And so now I have my balanced reaction and I can check it to make sure that it has the appropriate number of atoms of a particular type on either side. And if you do that, you'll see that that works, as well as the charge. So I have a +4 and 2 more is +6 on this side. So I better have a +6 over here. I got a +2 and a +4 here. So that's a +6 as well. Any questions on that? Here's some of the things that you should never do, and some things that you should do as far as balancing using the half reaction method. So you can read through these. And what I want to end up with in today's class or today's discussion is that balancing, that 5-to-2 ratio in the oxalate experiment. Um, so we're going to use this and use the half reaction method as an example to find the balanced chemical equation in an acid. Now remember, you added sulfuric acid in excess. You didn't know it from the procedure, but it was in excess in that reaction. So let's see how we would go about balancing this reaction. So I have to identify the reduction half reaction and the oxidation half reaction, but they tell me here, but say I didn't know that. Say I didn't know what was being oxidized and what was being reduced. Say they just gave me MnO4 minus plus oxalate. This is the reaction, right? 2 minus, and I know that it goes to Mn2 plus CO2. How would I know what's reduced and what's oxidized? I have to assign the oxidation states. So I do that -2. That's 8. So this has to be +7 to give me an overall -1. -2. That's -8. The whole thing is -2. So that's a +6 from 2 carbons. So each one of those is +3. And then +2 for the manganese ion. And I have -2 and +4 for CO2. Now I can see that the species that's being oxidized, I'm sorry, being reduced, the species being reduced is the permanganate, but the atom being reduced is the manganese, +7 to +2. Okay. For oxalate, I see that that's going to be, so this is reduced, and this guy has to be oxidized, and it is. So carbon goes from a +3 to a +4. So carbon is the atom in the species oxalate that's being reduced. So sometimes you'll see a question in homework or the book, they'll say what atom's being oxidized or reduced, or they'll say what species is being oxidized or reduced. So you can see the difference in what they're talking about. So species, that refers to, in this case, the reactant that can be an atom, it could be a molecule, it could be an ionic compound. You know, that's species is a general term for pretty much anything. All right, so we've identified our half reactions. So I'm going to split them up now into reduction and oxidation. So I said my reduction is going to be MnO4 minus, and that's going to go to Mn2 plus. And then my oxidation is going to be C2O4, 2 minus, and that's going to go to CO2. So what I'm going to do now is go through those steps for using the half reaction method for balancing. The first thing I want to do is balance all non hydrogen or oxygens. The manganese is balanced. So then I balance the oxygen with water, and I balance the hydrogen with acid. Okay. And then once I do that, it's time to add in the electrons for the charge. Or I can go down to the next one and do the same there. I think that's what the steps were, but uh, okay, let's do the next one then. Carbon is the non-oxygen hydrogen, and it's not balanced, so I have to put a 2 here. And now I have 2 oxygens on either side, sorry, 4 oxygens on either side, so that's balanced. I don't need any water, and I don't need any acid. Now it's time to balance the charge. Oxidation, I lose electrons. Electrons are going to go on the right. Reduction, I gain electrons. I know the electrons are going to go on the left. Now let me add up the charge. So I have 8 pluses and 1 minus, that's a net 7. And over on this side, I have a plus 2. So I have to bring that down from 7 to 2. So I have to add, anybody? How many electrons? I have a net plus 7 and a net plus 2. So if I add 5 electrons, that's going to bring this down to plus 2. Okay, so that balances the charge. Over here in the oxidation, you see that you need 2 electrons over here, and that'll balance the charge at a minus 2 on either side. Any questions? Okay, moving right along. Now it's time to make sure the total number of electrons lost equals gained. So I have 5 gained and 2 lost. What's the least common denominator of 5 and 2?
10.
Yeah, thanks. So I need to get 10 for both, and I know I can do that if I take all of this and multiply that by 2. And if I take all of this and multiply that by 5. So whenever you do these things, you try to be careful and neat as possible, not like me. Try to circle your oxidation states so you don't get them mixed up with your overall charges. Also, when you multiply through by factors, don't erase, just cross out. And then that way, if you make a mistake, hopefully it'll be easier to track down where that mistake occurred. So I'm going to multiply through by 2. So that's going to change this to 10. This goes to 16. 1 goes to 2. 2, 8. And then 5 down here. 5, 10, 10. Now I'm ready to add up and make sure that my total electrons cancel. And they do. So I get rid of this and this. And I add up everything else. So I got 16H plus 5C2O4 2 minus plus 2 MnO4 goes to 2 plus 10CO2 plus 8H2O. Now, sometimes you might have some water on the right and the left. You just have to see which one's larger and then get rid of the other water on the other side and reduce that number accordingly. You might have to do that with acid as well. But if you look through this balanced chemical equation now, you'll see that there's the same number of atoms on each side, and the charge should cancel too. So I have 16 plus minus 10 down to 6 minus 2 more down to plus 4 on this side. And on this side, I just have this guy charged, so I have a plus 4. So you see the charges are good. And if you check it out, you'll see that the atoms are good as well. Any questions on that? All right. The last thing that we're going to look at then is What happens when a question asks you to balance a redox reaction uh, in the presence of a base or in a basic solution, not an acidic solution? So instead of making up different steps for balancing using the half reaction method, what we tell people to do is just go ahead and balance it as though it was an acidic solution and then make an adjustment at the end for basic. So here I have our balanced equation in acidic solution. And what it says to make this adjusted for balancing in basic solution is just convert the number of H pluses that you have to water by adding that many hydroxides. Now, if I want to keep this balanced, then I have to add that many hydroxides to the right side. And I know what happens when I add hydroxides to H plus, I get water. So it'd be 16 H2O plus 2 MnO4 minus plus 5 C2O4 2 minus goes to 2 Mn2 plus 8 H2O plus 10 CO2 plus 16 OH minus. 16 of those. All right, so now this is balanced. But you know that chemists don't like it when you have the same molecule on either side. Like in this case, I have 8 waters over here and 16 here. So I just get rid of this guy and change this 16 to an 8. And now it's properly balanced. So you see that it's easy to balance things using that stepwise procedure in acid solution. And then if you have to use it for basic conditions, then just do this quick adjustment at the end. Any comments or questions on that? Okay. All right. So I think that's all I want to talk about today. Next time we'll start into talk about batteries and how it's related to the lab that you're doing. So.